So this is our egg in a bottle drop experiment. And what we did was we lit a piece of newspaper and dropped it into this bottle and then quickly placed the egg on top of the rim of the bottle. And the change in pressure due to the fire within the bottle consuming the oxygen caused the egg to be sucked into the bottle. Unfortunately, though, it was mainly the yolk that got sucked in, and this is the remnants of the outer white part, but it still basically was a success.
Salt and pepper are both neutrally charged, meaning they have equal numbers of protons and electrons. Protons are positively charged particles and electrons are negatively charged particles, and they're all in an atom, and there's the nucleus with protons and neutrons, and electrons go around it really, really fast. And protons are attracted to electrons because they're oppositely charged, but electrons are repelled from electrons and protons are repelled from protons, which is the basis for this experiment, which is separating salt and pepper. And what we're going to do is take a comb, and when you rub it in wool, it becomes negatively charged. And then when the negatively charged comb is brought to the neutrally charged salt and pepper, the electrons in the salt and pepper are repelled from the electrons in this negatively charged comb, because here all the protons are going into the wool, so it's going to induce a negative charge in the comb. And all the electrons in the salt and pepper are going to move to the bottom, leaving the protons at the top. And like this. And this is called polarization, and this is going to be a molecule of pepper. And when we bring the comb near the salt and pepper, the pepper is going to be drawn to the comb before the salt is, because pepper is lighter than salt, so the force doesn't have to be as great for the acceleration to be greater, because force equals mass times acceleration. So let's see. Oh, there's all the pepper going up. And if we bring the comb even closer, salt will begin to be attracted too. And these are all the polarized salt and pepper particles being attracted to the comb, because the positive from polarized pepper will be attracted to the negative here. And this is what happens. Ta-da. There's a correction we would like to make with the previous salt and pepper experiment. I said that when we rub the comb with the wool, the protons from the comb moved into the wool. This is incorrect because protons don't move. What happened is the electrons from the wool moved into the comb. According to the triboelectric series, which is a classification of how easily materials give up electrons, wool can easily give up electrons. So when it's rubbed with something like a comb, a lot of electrons move into the comb, and that's why the comb became negatively charged.
In a simple pendulum, the mass of the string and the object do not matter in determining period of the pendulum, nor does it matter in determining frequency, because frequency and period are inversely related. In the equation of determining the period of a pendulum, you can see that the length of the string and the gravity of the planet that you are on are the only two factors that truly matter in determining period. In this experiment, we will demonstrate what I just explained. Starting off with a whale that we have measured to be 30 grams and a string that we have measured as 18.5 inches long. Also, the angle at which you release the pendulum does not matter in determining frequency or period Anyway.
And period is the amount of time it takes for one full back and forth movement of the object, and frequency is the number of back and forth movements of the object in 1 minute. And period is measured in seconds, and frequency is measured in hertz. Ready? Go. 1.1 seconds is the period of Mr. Whale.
Now we will demonstrate it with a 80-gram banana.
That was 1.0 seconds. So you can see that they're basically the same. The period of Mr. Whale and Mr. Banana were the same, even though they were different masses. So now we'll try, and they were pretty much released from the same angle. So now we'll try both of them released from very small angles. And that was 1.1 seconds, which was the same as the other two trials.
Can I try from a really large angle?
Yep, and from a really large angle. That was 1.3 seconds, so basically the same. And we'll do the same thing for the banana. Really tiny angle. And that was 1.0 seconds. And 1.2 seconds. I mean, there's 0.2 seconds in human error, but I'm sorry, I can't be perfect. And units is going to change the length of the string from 18.5 inches to 12 inches. Magically. Whee.
And the period and frequency should change from our previous data, but the periods of the banana and the Mr. Whale should remain equal.
The period will decrease, and because they're inversely related, the frequency is going to increase because T equals 1 over F, and when one decreases, the other increases. So, ready? The period of that one was 0.9 seconds.
Now we will demonstrate it with Mr. Whale, and the period of Mr. Whale's cycle should be the same.
Yep, that was 0.9 seconds. So you can see they both decreased because the string was shorter, and that relates to the equation previously mentioned.
Okay, cool.
So in this experiment, we're going to show that two objects of different masses, Mr. Whale is 30 grams and Mr. Banana is 80 grams, when they're dropped from the same height, they'll hit the ground at the same time because the acceleration on Earth, no matter what, is going to be approximately 9.81 meters per second squared. And even though the force may be different because mass is different, the acceleration will be the same, so they'll hit the ground at the same time. So, here, ready? Ta-da! It burned a hole in the plastic.
Oh.
Oh, well, that's not good.
You want me to do it? Yep, let me see this. Wait.